Hi, and thanks for joining me in this video about icing. This video is one of many that I've recorded on icing. In particular, this one will look at induction icing. In our discussion of induction icing, first we'll start out by defining it. After that, we'll look at the regulations that the FAA has for induction icing. We'll talk about carburetor icing, inlet icing, and then finally high ice water content icing.
So induction icing is any icing that occurs with the power plant of the aircraft. Power plant, whether it be a piston engine or a turbine engine.
Part 23, which deals with the certification of light aircraft, has a regulation, that's 23.2415, that deals with power plant ice protection. And specifically, what it says is that aircraft design must include and be mindful of induction icing and also inlet icing. So they need to design these systems so that they can prevent foreseeable accumulation of ice or snow that will adversely affect the power plant. Also, it says that the power plant design must prevent any accumulation of ice or snow, and anytime an airplane wishes to be certified for flight into known icing conditions. The first kind of induction icing that we'll discuss is carburetor ice.
Carburetor icing is icing that forms with aircraft engines that have carburetors. And carburetors, of course, mean that the internal structures have venturis. There's also a throttle valve and other internal surfaces. So, in other words, when air flows through a carburetor, it encounters lower pressure, which results in adiabatic expansion, and you get little water droplets that form in the venturi that strike the throttle valve and freeze on contact. So it's not only the adiabatic pressure drop that results in the temperature drop, but also the vaporization of fuel. Remember that when you go from a liquid to a vapor, it requires energy. That energy comes from the air, so it lowers the temperature. So the combination of those two things, the drop in pressure and the vaporization of fuel, result in a significant drop in temperature. When that happens, the temperature drops down to reach the dew point. You get condensation droplets forming, and those will strike the carburetor and freeze, strike the throttle valve and freeze on contact. So you'll have the condensation and freezing on the throttle valve, also in the venturi. Sometimes it'll go straight from the water vapor phase to the solid, where you have deposition forming on the inside of the venturi. But typically it's usually water droplets that form and freeze on contact. And when that happens, it reduces the airflow going into the engine, and the engine is starved of air for combustion. So the conditions that are required, common conditions, you need typically high relative humidities or very high dew points. You don't need to have visible moisture. In other words, clouds and precipitation don't need to be present for carburetor ice. Just you need water vapor in the atmosphere. And typically when the engine is brought back to a gliding flight, that produces lower pressure in the carburetor, and as a result, adiabatic expansion and the condensation and freezing. Here are the most common conditions for carburetor ice. This is color-coded, and this came from an engine manufacturer. But you see temperature ranges anywhere from 80 degrees Fahrenheit all the way down to 10 degrees Fahrenheit. And relative humidities, typically the higher the relative humidity, the more likely your chances of carburetor ice are. But as you get to drier and drier relative humidities, the chances start to decrease. And for carburetor ice, how can you tell if you have carburetor ice? Well, the symptoms are if you have a fixed pitch propeller. In other words, if the propeller does not change the angle of attack, it's not adjustable, you don't have a propeller control, then you'll notice a loss of RPM and the engine will start to run rough. But if you have a propeller that can adjust, if you have a propeller control, then you'll notice first a loss of manifold pressure and then engine roughness, and eventually a loss of RPM. The antidote is carburetor heat. Apply full application of carburetor heat. The heat will be rerouted into the carburetor, start to melt the ice in the carburetor. That water is ingested by the cylinders in the engine. It'll make it rough run for a period of time, but then it will start to run again.
The next type of induction icing that we'll discuss is inlet icing.
So that is carburetor ice, another type of ice that can affect both turbine airplanes and also carbureted or fuel-injected airplanes is inlet icing. And inlet icing occurs anytime air is entering an engine. So for airplanes that have piston engines, then typically this is impact ice, meaning that when you're flying through visible moisture, water droplets are striking the airframe, and they're freezing on contact in the inlet of the engine, whether it be an air intake or even for that matter an air filter may ice over. So when ice filters ice over, when enough water is ingested and freezes on the filters, it'll clog the airflow going into the carburetor, or not the carburetor, but into the engine. And this can happen with carburetor airplanes, can also happen with fuel-injected airplanes. So the most common conditions for inlet icing is when you have visible moisture, in other words clouds and precipitation, and temperatures that are colder than 0 degrees Celsius, or in other words 32 degrees Fahrenheit. The antidote is an alternate air source. In other words, you have a control in the aircraft that will allow you to select another source of air for combustion. And if you have a carbureted airplane, you can turn on carburetor heat. That won't melt the ice, but it'll give you another source of air for the engine to use for combustion. And of course, the symptoms for inlet icing with an airplane that has a fixed pitch prop, you'll see a loss of RPM and engine roughness. If it's a constant speed propeller airplane, if you have a propeller control, then you'll notice a loss of manifold pressure and also engine roughness. With turbine-powered airplanes, it's not so much the airflow being reduced going into the engine, but it's more of a problem of ice forming on the engine inlet, and then that ice breaking off and being ingested by the engine and damaging turbine blades. This is a huge problem. There are checklist items that need to be followed that will allow you to turn on the engine anti-ice. And we had a case of this with our Cessna Citation. We had a double engine failure when the pilot, the captain flying, ignored the checklist and realized too late after icing conditions had been encountered that he forgot to turn on the anti-ice. So when he turned on the anti-ice, all the ice broke off, it entered the engine, and they had a double engine failure in cloud over the mountains. They survived, people walked away, but it was a stupid mistake on the part of the captain, and he was at fault. So the common conditions for inlet icing with turbine-powered airplanes, of course, is visible moisture and temperatures colder than 0 degrees Celsius. And of course, as I mentioned, the antidote is anti-ice. There are areas that are protected around the engines that are either heated with bleed air or some sort of electrical device to keep that inlet clean. Also, if you notice the Cessna Citation on the right side there, that picture, ahead of the engine is the wing, and you notice that the wing, the leading edge of the wing is silver. That is a hot section. In other words, it's heated so that no ice forms along the leading edge of the wing, and as a result, no ice will go into the engine inlet. Also, surrounding the engine itself, the entry into the engine, you notice that's also heated for both the turboprop and also the Citation, the pure turbine engine.
The next type of induction icing that we'll talk about is that which is caused by high ice-water content. Icing that's caused by high ice-water content is usually experienced only by turbojet or turbofan airplanes that are flying through the tops of cumulonimbus clouds or through anvil clouds. Those clouds are typically made up of ice crystals. The temperatures are very cold, and the number of ice crystals per volume is very high. In other words, the density of ice crystals is very high. So aircraft are experiencing lots of ice crystals as they fly through these clouds, and those ice crystals have the potential to create icing. This type of icing typically occurs at temperatures between minus 21 and 32 degrees Celsius. Usually there are no radar echoes. The aircraft are flying through the anvils of thunderstorms, dissipating thunderstorms. And as the airplane flies through, ice crystals striking the windshield will melt. But there is no airframe icing, and the only hazard is with turbine engines. Over the past several decades, there have been a number of aircraft that have reported degradation in engine performance, turbine engine performance, even flameouts and even engine rollbacks. So there are hazards associated with the collection of ice on turbine blades. And this is still a current research topic. They're trying to discover what exact conditions create these problems. And you'll probably find out more in the next few years. That is a quick overview of induction icing and the problems and hazards associated with it. Watch my other YouTube videos for other types of icing.